let's jump right on into things here. The first thing, I guess, if you want to call it a disclaimer, this is a summary of many, many things. We're going to see basically over 130 years of history, and obviously because of our time constraints, we're not going to be able to cover all of it. However, you're going to drink from the fire hydrant today in a lot of aspects, not only of printed circuit board design, but also technology and even quite a bit of world history as well. So the one thing you got to keep in mind is that I am going to gloss a lot of stuff, and really for every one major factor that I bring into this discussion today, there's going to be 10 things that I just going to either gloss over or completely dismiss altogether because I just don't have the time to go through it. So I do apologize if there's something you said, oh, we should have talked about that, or wanted to somehow you wanted me to go a little bit deeper onto one of these things over here. It's just there's a great deal to cover here, and again, we want to focus specifically on PCB design. So what is PCB design really all about? Well, in thinking about it, and when I initially came up with these slides for design for manufacturing, what it dawned on me is that PCB design is really about optimizing manufacturing of electronics. And you're going to see that over time, the PCB became from a nice, convenient way of doing manufacturing to something that's an absolute must. And you'll see an example in the mid-1940s where everything was done by hand. And as a result of the printed circuit board, our technology has moved in absolute leaps and bounds. And you can see that right here between these two examples. Here's an old calculator board. It's from the 1960s. All right, and we have some board over here. I just took a picture off the internet, and it's very typical of these high-density motherboards that we would see today in a computer or in another device. So we're packing more into our components. So for example, when you look at this board over here, you have 34 transistors. Each one of these cans is its own transistor, as opposed to a chip over here that's got probably over 1 million transistors alone in that one chip. We're shrinking the passives, so if you look at one of these through-hole resistors, now we're talking about 0402s and things that are even smaller. So 4 of these could easily fit where one of these is currently residing on this older board. And of course, increased component density on the board. Everything that you see over here could probably be easily represented in one of these chips. And there's probably more additional capability to spare even within one of those chips. So it's really amazing how we've been able to miniaturize things over time and get more capability out of our designs. What is it driven by? Well, it's driven by overall speed of the product, the functionality of the product, and the cost to assemble and manufacture the product as well, and a decreased cost and time. Okay, I want to make sure there's something here because we have a poll coming up, and I want to make sure it worked here. So the increased overall speed of time. Let's face it, we expect things to happen very, very rapidly. And we want when we put something into our device, we expect an immediate response. Even a couple of seconds irritates us. Increased functionality of the product. Look, you know, when I was a kid growing up, I had a little Space Invaders handheld game. Now that would just be mundane to me. I would expect a whole bunch of different levels. I'd expect bonus levels, different points for doing things, a whole lot of control functionality other than left and right and a fire button. Increased cost of manufacture and assembly. You're going to be amazed at how much we get for we get a really big bang for our buck, and that's what our poll question is going to be here in just a moment, and a decreased time to manufacture and assemble. And you have to keep in mind that something like this television set over here it probably took them about a year to develop it and a year to get it out there. Now we don't have years. We have possibly months, but more likely weeks to get something manufactured and assembled and out there as quickly as possible, or we're going to miss the market window. So let's take a moment here to compare these two television sets that you see up here. So we have an RCA CT100. It's a beautiful looking antique here. It was called the Miro model, so back then they would give these things these nice model names for their advertising and marketing. 1954 development, okay, or it's model of 1954. 15-inch screen. I don't know if that's considered to be diagonal or from left to right, but the fact of the matter is they consider it to be a 15-inch screen in their advertising documents. 16 channels, okay, because the knob here was set for 16, and it was actually a color television. So if you could pick up a color broadcast, this television could actually show it in color. It was priced at $1,000 in 1954, and it has no remote. Okay, so that was considered to be state-of-the-art at the time. Now we take a look at this Samsung, for example, and I just picked one at random because I just wanted to pick out what is, let's say, a common television set for our day. It's the Samsung LED. Obviously, they didn't give it a very pretty name over here. we have to keep in mind that Samsung probably builds a couple 100,000 of these and then moves on to a next model number very, very quickly, or they're custom building them for certain chain stores. Maybe Costco has a certain version of it, Best Buy has a certain version of it, and so on and so forth. So these numbers probably have a very meaningful representation as opposed to a lovely model name for it. This was apparently available here in 2015, at least when I put this presentation together. I could buy it from Best Buy for the price shown down here. 49.5-inch screen. Most of us know that there's easily 80-inch screens and bigger than that, so this is not necessarily the greatest or the biggest and the best that's out in the market, but it's certainly a large size. You can get hundreds of channels out of this as opposed to 16 channels, especially if you have something like satellite television or cable television. The color is just unbelievable, right, as opposed to simple RGB and having the mixture of it. And it sells for $750. And that brings me actually over here to my polling question, and that is, if I was to buy this in $1954, how much would it cost me? So if you take a look at your polling, and it'll come up here in just a moment, okay? If you take a minute to just guess which one you think it is, do you think it's less than $100, less than $500, less than $1,000, or greater than $1,000? So if I was to use $1954 to purchase this, okay, how much would this cost? So things are coming in here, and the results are interesting. I think everybody's trying to figure out if there was inflationary considerations to this. I think we've got as many votes as we're going to get at this point in time. So the dollar value of this in $1954 is actually, get this to roll here, is $112.72 in 1954. So basically, what's amazing about this is that you look at this television set, which cost $1,000 in 1954, and in that same amount of money, in today's value, okay, or probably 1954 value, you get all of this for 1/10 of the cost. So what does that mean? It means our manufacturing and our ability to get technology out there is phenomenal. We really move technology out there. We've made it as cheap as possible, and it's going to continue to go down that way. And by the way, the remote is included in that. So the answer to this was B, by the way. So I know that a lot of people put down 38% put down less than 100, and that's pretty close to it. I was thinking more, when I did this survey over here, I'd have to admit I probably should. I was thinking about doing 112, and then I said, let's just try to keep it to round numbers here. So if you did pick A or B, you're definitely in the ballpark. All right, so let's get on over here with the history of it. We need to actually start in the Gilded Age, and the Gilded Age is from 1870 to 1900, and the Gilded Age is really the American Industrial Revolution. So it's not the revolution itself, it's the Industrial Revolution. We've just gotten out of the American Civil War. That was in the 1860s, and now mass manufacturing is really taking a hold in the United States. So we're actually, what we were going through between 1870 and 1900 is exactly what China is now actually going through right now. So we had our kind of heyday 140 years ago. So we were manufacturing everything, food, clothing, furniture, you name it. The one thing we weren't doing during this period of time was cars. So even though cars and the concept of the gasoline engine were starting to come about, the assembly line itself, which was created by Henry Ford, didn't really come about until 1913. So it's not considered to be a part of the Gilded Age. In terms of transportation, there was a ton of track that was being laid down between the west coast of the United States and the east coast of the United States, so they're trying to get goods and service across the U.S. And really their level of engineering triumph and technology was the ability to get someone from the east coast to the west coast in 5 to 7 days, as opposed to 5 to 7 months on basically a horse and wagon. Okay. The key discoveries during this time, and there's quite a few of them, but the ones that are most important to us because they really impact each and every single one of us here in this webinar, is the discoveries in electricity. Now, we didn't discover electricity at that time. Electricity and its properties were being discovered well before that, but now what you're seeing is a commoditizing of electricity. We're doing something with it now other than just doing lab experiments. We are piping it, basically we're piping it into houses. Now, this didn't all happen at once. This is something that took almost about 100 years, I would say more like 75 years to happen. It primarily happened in the cities. It moved out to the suburbs and ultimately made itself available to the rural areas of the United States, primarily after the Second World War, which is in the 1940s. And then there's also discoveries, oh, by the way, I should mention here that this became a phenomenal alternative for coal, wood, and oil. So at the time, if you were living in something like New York City, you had to basically heat your home, and you also had to cook. And the methods you could do is you could purchase coal, which was very sooty, wasn't very good to work with or not easy to work with. You had wood. Now keep in mind, when you have a large population together, in order to use wood, you've really got to cut down a lot of trees in order to maintain that level of firewood in order to have everybody cook and clean, do what they need to do with by boiling water and cooking their food, or you can keep in the house warm. And lastly, with oil. And what's interesting about the oil, and I'll take a step over here and go on a little bit of a tangent, a lot of people don't realize this. Now, in the United States, there was a company called Standard Oil, and it was a massive company. It was a total monopoly. It was owned by a fellow by the name of J.D. Rockefeller. His ancestors are still out there today, kind of keeping the legacy somewhat going here. But Standard Oil was a trust, and a trust was basically a conglomeration of corporations that were owned by the same, or basically owned by the same people, and they monopolized things. Ultimately, that trust was broken up, but the interesting part about this was that the oil that Standard Oil made its money off of was not for gasoline for cars and for airplanes and stuff, and for motorized vehicles, which they now make their money off of. Standard Oil is now pretty much ExxonMobil. But what's interesting about this is that they made most of their money in providing oil that could be burned for both cooking by boiling water and frying whatever else, and also for lighting as well. So now electricity was kind of coming into the scene over here as an alternative to these three things. And interestingly enough, it was pushing out oil. However, of course, Henry Ford with his Model T and assembly line over there gave a new meaning and purpose for Standard Oil. So they were now going down the path of creating gasoline rather than kerosene for the houses. Discoveries in electromagnetics. Big thing was motors and generators. So just a reminder that a motor is basically taking electrical energy and converting it into mechanical energy, and vice versa. You got generators in which you're taking mechanical energy and turning it into electrical energy. So these are now becoming services and commoditized products. During the Gilded Age, you had a number of major inventors. The two that we're most interested in is Thomas Edison, obviously the light bulb, which really ushered in our profession, because he was big on the light bulb. And with Edison, and I'll talk about this in a couple of minutes, he wanted to sell you everything, not just the light bulb. He wanted to sell you the services as well. And I'll talk a little bit more about that later on. Obviously, Edison is known for much more inventions, many other things other than just a light bulb. The other big things, the movie, the phonograph, and so on and so forth. He has hundreds of patents to his name. His arch enemy and rival, Nikola Tesla, he was credited for actually the motor and also for AC power. So just a little side story to give you about these two guys over here is that Nikola Tesla came over to the United States. He got a job with Thomas Edison and worked for Thomas Edison for about a year. And Edison challenged Tesla to work on something. And if he got it to work, he would get $5,000, which is a lot of money at that time. And so Tesla really took it to heart, and he actually was able to make this thing work. So when he presented it to Edison and asked him for the $5,000, well, let's put it this way, Edison basically kindly told him to go pound sand. So Tesla kind of left Edison in a huff, and then later on, they got into the great battle over how you're going to do electrical transmission over lines. So Edison was a big fan of DC power. Nikola Tesla was a big fan of AC power, and ultimately Tesla won out because AC tends to be the better method of basically getting energy from one place to another in long distances. The one thing I do find interesting about all these things is that in the end, we're always dealing with AC and DC issues. AC may be great for transmission, but here in our houses, anytime we plug in a device, either that device is large enough to have an AC-DC converter to it, or we have a wall wart that converts it to DC. And even more interesting about it, and I think it's kind of something that has to be really thought through, when we look at solar panels, for example, solar panels collect in DC, which in turn has to be put AC onto the line, which in turn we turn back into DC in order to power our appliances. So it seems like we're losing a lot of efficiency going between AC and DC, but just something to ponder on the back of your head. Other major inventions, just of note, the telephone came out in 1876. Eastman Kodak came out with the camera for the masses. Very large things, couldn't take selfies with them, but nevertheless, pretty cool to take a look at. You know, if you ever see those pictures, and it just made cameras available to families and those people who wanted to actually make a living off of photography. Herman Hollowith here just mention the tabulator because ultimately his product and his business becomes IBM. Now, in the midst of all of this, this sets us up for one of the first, call it PCB inventions out there, at least patents. Now you'll notice also the date has changed over here. We were talking about the Gilded Age, which was from 1870 to 1900. Now you start seeing the Progressive Era, and there was an overlap of about 10 years. The Progressive Era was about trying to basically reform a lot of the issues that were going on at that time. For example, the child labor laws were passed. The Sherman Antitrust was passed, so they broke up Standard Oil. So they were trying to do these things to kind of quote-unquote fix some of society's ills. Nevertheless, during this period of time, we start seeing the first concept of the printed circuit board. And it's in 1903 by a fellow by the name of Albert Hansen. He was a German inventor, and he got a British patent for this. And what's interesting about this is how it is described. It's flat foil conductors, okay, which you see over here going from A to B, to an insulating board in multiple layers. Well, that basically describes the modern-day PCB. Okay. In addition to that, what he also describes is the concept of through-hole. So what he was saying is that not only do you have these wires over here running in parallel to an insulated board, you also run them also in parallel on another layer, but these two layers would be perpendicular to each other, so if you know where their contact point is, you could punch a hole in it and make connectivity to them. And I thought this was really cool. The only problem is I couldn't find any invention that actually used it. And as a matter of fact, I think it was just somebody going through various inventions realizing that, hey, this guy actually came up with the concept of the PCB. But again, you'll see later on that these ideas kind of get rehashed in different patents. All right. Now, one of the problems that you had in this particular time is that, well, first and foremost, let's talk about what products were being made. What were people doing with this electricity? The big one was the industrial applications. Anything that you could make your machines faster, if you didn't have to throw coal at it, anything that you could do to make your industry move or your assembly lines move faster, they were applying it to that because that's where the money was. Definitely lighting, that's what Thomas Edison was all about, and I'll talk a little bit more about this in a minute. And then, of course, the other products of that is heating and cooking, and a lot of times those go hand in hand together with each other. The biggest problem that you had was that there was no standardization. And that was because of the idea that Edison had. Edison just didn't want to sell you a light bulb. He wanted to sell you the whole service. And so what that meant is that he said, look, if you want my electric light in your house, you will pay to have this service hooked up, and you'll pay me a monthly fee for the electricity that you use. And if you need a light bulb, you'll come to me and you'll purchase the light bulbs from me. And all these other things that kind of came about were what you'd call add-ons. And as a matter of fact, if you look at it, look at how you would plug these appliances into your outlet. Well, your outlet was actually your light socket. So here's an example. This is from General Electric. It was a heating plate, and you can see that this heating plate was actually hooked into the light socket. I don't know where they got the light from because they took the light bulb out, but apparently it would still work, obviously, to warm this up. And then, of course, here's an example over here, and I don't think I have a quiz for this one, but this is actually an electric toaster. And so if you do come across any antiques where you see this type of a connector at the end of it, more than likely it's prior to 1920. So that's definitely an antique to take a look at. But now, what was the problem? Well, Thomas Edison definitely ruled New Jersey and the New York area, but there were other people doing similar things in other cities, and they were coming up with their own standardizations. There was one that was called the Chapman one. And so as a result, you didn't have products that would work with each other's configurations because they would purposely make their sockets different. So here's an example of that right over here. I think they call this one a Chapman version of it. So we have to thank a fellow by the name of Harvey Hubble. And Harvey Hubble was the guy who basically standardized us on the wall outlet here in the United States that we know today. So he patents that in 1915, and that's the one that will take off from there. So it ends this problem of having to unscrew your light bulb so that you can plug in your heating plate or your other appliance, because obviously if you're doing that, you're now in the dark, especially at night. One thing I will mention, though, is that the modern-day light bulb that we have today, the screw-in ones that we have, that is Edison's standard. That's the one that Edison came up with. That one is the one that became the standard method for light bulbs. So even though there were other ones at that time, everybody eventually said, no, we got to have one standard, and that's the one we're going to use. And by the way, that the U.S. wall outlet itself didn't really become what you'd call codified by NEMA until 1934. All right. During this progressive era, we see World War I. come about. July 1914 to November 1917. The United States joins it late. They join it due to the sinking of the Lusitania, and the rest is history at that point in time. What you're going to see with these pictures over here is that this was a very, this war was based on mechanical devices more than anything else. They did use trench warfare, chemical warfare. From all the stories I've ever read about this war, it was a miserable war to be in, just because of the trench warfare. You're hiding in a ditch for months at a time, and the battle lines really didn't move one way or another. So what you also notice here is just the minimal use of electronics at this point. It's still very much mechanical. We get into what's called the Roaring Twenties. So after the First World War, we start seeing an economic boom in the United States, a lot of exports going over to Europe, since a lot of Europe had been devastated by the First War, and our production is just really ramped up just as much as it had been in the past. So the first time, and this is a big thing because this has a big impact on electronics, the first time in the U.S. that more people live in cities than on farms. So that's the first time in the United States that actually happened. You're also seeing the beginning of chain stores. Chain stores are starting to show up across the entire United States, whereas in the past you may have had a city that had one or two of the stores that were owned by the same family or business. Now you're seeing them across multiple cities. So the idea of chain stores are now coming in. National branding and products, things like Coca-Cola or Nabisco, which by the way stands for National Biscuit Company. You're starting to see these national brandings go across the U.S. And if you think about it, at that time, it's kind of what we think about now, that a lot of times we create a product, we think about, wow, we got to get this out internationally. Let's get this out to the U.S., and let's get this out to Europe, and let's get this out to Asia, and let's get this out to Australia, right, and so on and so forth. So they were battling with the same concepts 100 years ago of how do we get all of our products to all the cities across the United States. The biggest thing here is the automobile and its infrastructure. And one thing I've noticed when it comes to technology, it's one thing to have a new product. It's another thing when that product requires an infrastructure to go along with it. And if you think about it for a moment, in the 1990s, we had two major infrastructures that required our economy to really focus in on it, and it really was a boom time for us. We needed more. We had the information technology, and everybody wanted a computer, and they wanted to hook it up so to talk to each other through the internet. So we had to build a huge infrastructure for that. We had to build switchers and routers. There had to be a ton of fiber optic put into the ground. All these different services came up to sell the ability to get onto the internet, all the software that was being written for it. So there was a big infrastructure for that. Same thing with the cellular system as well. Automobiles were no different. So automobiles, for example, when they came out, all of a sudden people said, look, our roads are just nothing but mud paths, and these vehicles just don't ride well on them. Let's pave our streets. All of a sudden people needed gasoline, so service stations showed up. Hey, these cars, you know, they had wear and tear on them, so now there was all these service stations to fix these automobiles. There were knickknacks and clothing wear that you could wear for your Sunday trips out. So there was a huge infrastructure that was built due to the automobile. Okay? And of course, building the automobiles themselves, and there were several major car companies that were created in order to do that selling of automobiles. And of course, because all this money is coming about, there's also the selling of appliances. And again, because a lot of people were living in the cities and they wanted the conveniences of those appliances, some of it out of necessity. All right, so here are some appliances that you see over here, and I'm going to ask to get the next poll queued up over here. Let's talk about a few of them first. The first one over, actually, take a look at this one, and then as I'm doing this, I'll talk about some of the other ones. This is a very, very interesting device over here, and so the polling question that we have over here is, what is it? Okay, so take a look at that moment. So is it a popcorn machine? Is it a waffle iron? Is it a toaster? Is it all of the above? So take a look, and I'll reveal that in just a moment. But in the meantime, some other things to note. So the washing machine finally comes out. I don't know how people live without one of these things, but the washing machine was out there. Also, you see vacuums coming out, and you also see refrigerators. So for the first time, so people are now able to use refrigeration. They could go to the store and buy perishable items that could last a couple of days, rather than having to constantly go to the store to buy things because of the freshness issues. Okay. So we've got a couple of things coming on over here, and it looks like a race between D and B right now. A couple of other people venturing guesses on A and C. Okay, I think we've got all our votes over here. So the count over here was 8% for the popcorn machine, 33% for the waffle iron, 11% for the toaster, and 48% D, all of the above. And believe it or not, it is D. So it was a 3-in-1 device. I'm almost surprised that someone from the As Seen on Television crew hasn't picked up on this idea and tried to sell it as some type of retro/antique kind of fun device. Anyways, but that's what it was. It was literally a 3-in-1 device. All right, so let's talk about printed circuit boards. So far, no printed circuit boards in any of these products. But in 1925, Charles Dukas submits a pattern for adding conductive inks to an insulating material. And interestingly enough, this method that he uses becomes very popular in the manufacturing of a lot of products. And it gave birth to the term printed wiring board, or PWB. So he's actually credited for this. And some people will say, well, I know that Mr. Hansen in 1903 seems to have come up with what is considered to be the modern day printed circuit board, but here's really almost the first application of something that is resembling a printed circuit board. And it was primarily used to as a flat heating coil for various products. So keep in mind at this point, most of the electronics weren't there to communicate with each other. Most of the time it was to send a current through it to either light something or to heat something. Okay, but I want to take a side note on this because I think this is a point of confusion. It certainly was for me for a while, because you always hear these terms PWAs, PWBs, and of course we use the generic term PCBs. So if you work for a company that's really large, or one that's been around for a long time, you're probably familiar with the concept of PWAs and PWBs. And really what they stand for is printed wiring board, which is basically an unpopulated board, which is what you see over here in this picture, and a PWA, which is a printed wiring assembly, which means it's basically a populated board. And of course, I see PWA and PWB, and I almost think that they'd be flipped just because of the order of the lettering. But no, PWBs are generally the unpopulated board, which come out first because of fabrication, and then PWAs will be second because of the assembly that's done to it thereafter. All right, 1930, we get into the Depression years. And just very quickly, 1929, Wall Street stock market crash. So all these great inventions, innovations, it all kind of came to a crashing end. And unfortunately, the Great Depression, which lasted 10 years, 25% unemployment, 25,000 banks failed, and it was certainly felt worldwide. It was not just a U.S. phenomenon. But what happened there is because of this crash, ultimately, it created an opportunity for the rise of infamous leaders like Hitler, Mussolini, Stalin, and others, which will lead us here into World War II. So World War II, why is this important in electronics? Well, you're going to find out here in just a moment that the first PCBs that you and I, as we know them, make their introduction. So 1939 to 1945, and the U.S. enters this war in 1942 because of Pearl Harbor, which was bombed in December of 41. There's two things to note over here. Number one, this is totally a mechanized war. So cavalry is out. The trench warfare isn't happening anymore. They're just basically sending machines after each other. Obviously, they're not automated, but they're basically it was machine against machine in most of this here. And a good portion of this has to do with communication. The reason I put this up here is that if you're ever interested about the whole Pearl Harbor incident, a portion of the movie is obviously showing the attack of Pearl Harbor itself, but a good portion of the beginning of the movie is spent talking about all the comedy of errors that happened in an attempt to communicate with Honolulu that this attack was imminent. There was information that they felt this was going to happen. They wanted to get information to them to say, look, you better prepare. We think something's going on the horizon here. And every attempt that they had to try to contact Honolulu about this happening just fell flat. And as a result, it really did catch them by surprise. And because of that, the Department of Defense did, here in the United States, realize that communication was absolutely imperative, and thus set them on a course to look at electronics as a way to communicate to and from places, and to make that a part of their regiment that, hey, look, we need to know where our folks are. We can't just be doing things through Morse code or through wires. We've got to be able to communicate, and that's where they start getting into the electronics, and you're going to see that here now. So during World War II, the very first use of a printed circuit board, as we know it today, was used in something called a proximity fuse. Okay? And the proximity fuse was a concept for weapons that now had to fire at greater distances. So we're no longer lobbing cannonballs at each other. We're now firing at targets that are in the sky, like aircraft that are miles above or thousands of feet away. So we also not only want to fire at greater distances, we need to hit very specific or smaller targets. And so that's when the British came up with the concept of the proximity fuse. Now, you got to remember that during World War II, Hitler basically took over all of Europe, and then he was bombarding London and the British Isles. And so the British had to come up with defensive mechanisms, and one of the things they came up with was the proximity fuse. They did share that with the United States in order to help us make in cooperation so that they could use our manufacturing to help assist with this. And the United States actually did perfect it for high-velocity artillery shells. Okay? And as I mentioned earlier on, the fuse is made using printed circuit board concepts that we know today. I was trying to find an example of one, but apparently the proximity fuse was considered to be a technological advance equal to the atomic bomb. So it was kept under very, very tight wraps, and I cannot find one. I think that this is a later version of the concept, but obviously I don't even know where the printed circuit board is. I'd have to go look around in here. But that's the idea of the proximity fuse, and that's the first introduction to the PCB. All right. In addition to that, we have a fellow by the name of Paul Eisler. He's an Australian out of UK. So in 1936, he gets a patent for copper foil on glass reinforced non-conductive base. That's core material, right? The idea of taking an insulator and then rolling copper on the top and the bottom of it, he's basically the one who was given the patent for that in 1936. He takes it one step further, and he actually makes a radio out of this in 1943, and here's an example of one of his radios. So you can finally see here's the insulating material, and here's the copper that is etched out of it. So now you see another example, again, military purposes of printed circuit boards being used. Okay, let's get into the post-war 1940s. So what are we seeing? The baby boom generation, so all U.S. servicemen, they're coming back from the war. They're trying to start their families. They're having a lot of children. That's why we call it the baby boom generation. It's improved in new appliances. So there are appliances already out there, like the vacuum cleaner and the washing machine, but they're getting now improved. You're now also seeing television sets and even for a period of time radios. Now radios had been around the 1920s, and of course they were certainly around the 1930s, but just keep in mind that during the Depression, a lot of people simply couldn't afford them. In fact, most people couldn't even afford the food on their plate. So the radios, they were there, but it was really more purchased in the 1940s. And then, of course, the television set really took off in the late 40s into the 1950s. So now you're starting to see, again, a lot of purchasing of appliances, but still you don't see printed circuit boards in there just yet. What you're seeing over here is an example of something called a Dumont model RA103 television/radio, and this is how they built them. And you look in there, there's no printed circuit boards, but you can see that this is a very, very tough way to make it. This all had to have been done by hand. You can only wonder how many opportunities there were for field failures in this. So you can see that this thing is just screaming for a printed circuit board at this point in time. Now, that was going to come soon enough because of the transistor. 1947, the first transistor comes out of Bell Labs, and by 1953, the first transistors are used in commercial products. So it took 6 years to go from the labs into commercial products. Now, keep in mind, again, they didn't have the internet then, so if someone makes a great discovery like this, they've got to get it printed into the journals. People have got to read the journals. They've got to attend conferences. They've got to think about how to use this thing, got to design it into their equipment. So it took 6 years for it to propagate. Now I think it takes about 6 hours, but you know, you got to keep in mind that there was no internet back then. We tend to forget the way it was before the 1990s. Manufacturing incorporates PCBs into their products as holding devices. So even if they did use printed circuit boards, they didn't really have connectivity. They were just using them as a convenient way of basically putting components together so that they didn't have to do this wire connecting the way they were doing in this particular box. And obviously the number of components and reduction in component sizes were starting to drive people to using printed circuit boards. Now, we talk about the Cold War era, which historians claim started in 1947 to 1991. I'm not going to argue that at this point in time. Those people who've lived here in the U.S. should hopefully remember the Cold War era. This was a time when the Soviet Union and the United States were really kind of going head-to-head with each other, primarily based on their ideologies. It was capitalism versus communism. And there was a number of times where we actually almost went to war with each other. Fortunately, that didn't happen. But the United States Army really had to start beefing up its ability to understand what the enemy was doing and to communicate with each other in fast ways possible. So one of the things that they did was they released their patent for the process of assembling electrical circuits, aka the etching of copper, to basically, I think, primarily for the defense contractors, but anybody else could use it if they so saw fit to do so. Okay, and as I mentioned here, the PCB in the past, if they were going to use it, was just a holding device with it didn't have connectivity, but now you actually had connectivity into it. There was no via hole capability, so obviously they didn't read the 1903 patent by Mr. Hansen. And it had to be created with, when you did the connectivity, you had to be very creative with it. So you'll notice over here with this design, I thought this was a really cool design, there are no crossovers. And if you needed something to cross over, you had to be very strategic about how you placed your component, so the component itself would act as the crossover. So that was the technology at the time. Some people, and I don't remember if I saw this or confirmed it or not, but this may have also been the process they used for that device that we talked about from World War II. I forget what they called it now. It was the, let me flip it back here. The proximity fuse. There we go. It was the proximity fuse. So I think that they stated this was the process they used for the proximity fuse. All right. Now, so we start getting into the Cold War era, and in particular the space race. So in the 1950s, late 1950s, the Soviet Union starts leading the space race in several ways. They're the first ones to launch Sputnik. They're the first ones to launch Lunar 2, which is to hit the moon, and they hit it. And then the first cosmonaut, Yuri Gagarin, is the first one to actually human, and she went around the Earth and came back down safely. So was the U.S. doing these things? They certainly were. However, they were always about a year or two behind. And they realized that if you could get up to space over here, you had air superiority. They were very concerned about the Soviet Union putting weapons above the United States, and so they felt that they had to get up there just as quickly as the Soviet Union was getting up there. So here's the deal. 1960s, the United States increases its space budget by 5x. Okay, so they kept increasing that budget, and then, of course, in 1962, the infamous Kennedy speech at Rice Stadium on September 12th about we choose to go to the moon. And then on the 20th of 1969, we land on the moon. Now, I know that there's some conspiracists out there, and I'm not going to go there, but I can tell you this. The United States did spend a lot of money, and there was a lot of research done for the military. And as a result of that, we get some of the things that we now have in our printed circuit boards today. 1963, Hazeltine Corporation patents through-hole technology. Okay, so yeah, again, we saw it in the 1903 patent, but this is a very specific one where you drill it out and you plate it. Okay, and it allows for closer spacing of components now, so now you didn't have to play these games of trying to avoid crossovers, and it was driven by increased IC development. We'll talk about integrated chip development here in just a moment. Also during the 1960s, we see the beginnings of surface mount technology, or SMT. IBM is primarily credited for that. You're soldering directly onto the pad, you're not drilling holes. And its actual first practical use was the Saturn rockets. All right. I know that this picture, and actually this picture and these pictures over here are not from the 1960s, but what I wanted to emphasize over here is the concept of the SMT, which you probably have seen. Of course, now you're making things that are much more densely packed together, because now you can allow for denser pin counts and denser real estate usage with them. In the 1970s, not just the dial and microprocessor, but we're seeing more and more ICs. We're not just having individual transistors or components. We're putting things together for different capabilities. And what you have here is 1958, a fellow by the name of Jack Kirby in Texas Instruments develops the first IC. Jack actually was a newbie at Texas Instruments, in my understanding, if I read the story correctly. He had been on the conversations in regards to the concept of ICs, but since he was the low man on the totem pole, he kept silent because there's somewhat of a pecking order back then. And the senior engineers were sent out for a week. I don't know if it was for a conference or for a sabbatical, but he basically ran with an idea in his head, and he spent the week doing it. And when they came back, he showed them what they had done. They fell in love with it, and now he's credited for the first IC. And by 1970s, very commonly used in manufacturing. And not only used in manufacturing, anybody who wasn't using a printed circuit board at that point in time was in big trouble, because the hands, with the number of components and the complexity of your devices, it just was becoming too difficult to do things by soldering wires onto resistors and capacitors and other discrete components. 1980s, we start the digital age. This is when I come into being primarily. So these are the things I certainly remember. Obviously, everybody's starting to buy personal computers. You also see a change in our media, meaning terms compact discs and also VHS. We have, you can now go to a movie store and rent out a movie rather than wait for it to be shown on television or go to the movie theater to see it. You also have what I call dedicated devices. So a camera was dedicated to recording. A game system was dedicated to gaming. This over here is just a handheld version of a gaming system. The Walkman was dedicated to music. So you have dedicated devices. And of course, game consoles as well, which is a dedicated device. But this is where they did exist in the 1970s, but they really took off in the 1980s. In the 1980s, we started off with the concepts of drawing by hand. So here's a picture of a light board and the ability to draw it, and these are what they called puppets from Bishop Graphics. And I took these pictures from a wonderful fellow by the name of Bill Brooks, who is a friend of mine, and he actually grew up doing printed circuit boards. His father owned a design house, and as a teenager, that's how he made his money, and so he's got some really wonderful pictures of those things. So if you're ever interested, go ahead and take a look at his site over here. But this is the way they did it before EDA. So by the end of the 1980s, really the drawing boards went away and everybody moved on to computers. So you had computer-driven layouts. You also had the Gerber format, which was established in 1980. So you'd send out a disk to the fabricator. They could feed that into their machines, and they would be able to do your lithography and fabrication. You definitely were getting tighter tolerances because of that and faster design times. And one thing I should note over here, and I noted it here, but I'll make mention of it as well in this prior slide, you would draw these out and then you take a photograph of them. As opposed to now, you would basically have the computer, you put it on disk, and you would have a text file that would have all these coordinates, and that was being fed into the machinery. Now in the 1990s, and this is when I start working, is you start seeing the BGAs, and I was actually kind of in the thicket of these things when they first came out as a test engineer. So BGAs come out, and not only just the BGAs in terms of packaging, but also silicon is shrinking at just a marvelous rate. Incredible what you could now put on silicon, which in the past was in microns. Now it's in submicrons now, and even much smaller. But you're getting smaller gates, more gates per chip. You're also embedding memory, and you also had systems on a chip. So no longer just one function, but multiple functions on the chip. You also had embedded memory as well. And just a very quick story about this. When I worked in the test group, we got some memory in from Canada, and it was held up by customs. And the reason they held it up is because the way they described it is that it had memory. And a couple of years earlier, there was a lot of memory dumping done on the United States by Japan, which drove down the price of memory, which in turn put out a lot of businesses in the United States. So the government responded by putting tariffs on it. So this got held up because it said memory, and I had to explain to them that this memory had to be a part of the silicon and that you couldn't salvage the silicon. And I was looking for that memo because I thought it was kind of an interesting explanation I had to give, but in the end we did get our components. But this is the beginning of the idea that, hey, we have so much real estate on the silicon now, let's embed the memory in it. We get into BGAs, and this brings me to my third polling question, and the third polling question is this. How big do you think, or how many pins do you think that this BGA is? Now this other chip over here, which was the prior revision, and it was for a mainframe computer for Unisys, this had 491 pins. Obviously it's much larger. So how many pins do you think this one is? I'll just give you a few moments here just to throw some numbers at it. So while you're doing that, just give a little story of this. When I started out of college, this is actually a stock photo that I have. When I started out of college, I worked for Cadence Design Systems. I was doing work for their design group, and actually my desk was at the Unisys Corporation here in Rancho Bernardo, California, which is a suburb of San Diego, and eventually did close down, unfortunately. And these were the last generation of Unisys mainframe computer chips. Okay? And at the time, they had taken a picture of these things, and when they were kind of closing up shop, they were going to dump them, and I got a copy of them, and I scanned them in because I thought they were quite a piece of history. So that's, but I used to work on these. We used to test these components, and that was a part of my job when I first got out of college. All right, I think we got a few things coming in here, and the answer, I guess a few more people are going to throw a few more questions at it, or pardon me, answers at it. Okay, well, I'm going to tell you it's actually 600 pins. So this is a 600 pin device here, as opposed to a 491 pin device. And by the way, this one over here is wire bonded, as opposed to this over here, which is called a flip chip. You can't see the back side of it, but you actually take the chip, you flip it around, and you solder it onto, or it's put through through a heating device, and it actually gets soldered onto the package itself. So what's the point about saying all these things? Well, everything miniaturized at that point in time. So even though we don't necessarily see, the equipment was improving, but we didn't see any new features to the printed circuit board itself, other than the fact that things are getting so small that now we have to be smarter about things. Things like new test strategies for designed for tests, where in the past you might have taken a board, you may have even been able to pop off one of the components, you may have been able to blue wire things, tombstone them, dead bug them. It was a lot easier back then to do that. Now with the way things are and how small they are, especially with the BGAs, that's really, really difficult to do, if not impossible. So if you are going to build things that are that dense, you've got to have your strategies ready for design for test. We talk about this in the pre-layout considerations webinar. Also, we designed it with, you need to design it with rework in mind. So if you're planning on pulling something off, you've got to have that foresight to say, you know what, if rework is required, these are the things that have got to have to be placed in a certain way or removed so I can actually get this thing removed. And of course, increasingly difficult to hand solder. You look at this 0402 and 0603, and these are the actual sizes. I mean, it's really hard to get tweezers on them, let alone try to solder those on. So what we're seeing in the 1990s is a huge miniaturization of things. Where do we go from here? Well, what's interesting about things now is that when I was looking up saying, well, what's this new era we're in? Obviously, there's been a lot of changes. And I was kind of calling it the Hitchhiker's Guide to the Galaxy come true, because they were talking in the 1970s when this book came out of a handheld device called the Hitchhiker's Guide to the Galaxy. And it dawned on me that my iPhone is the Hitchhiker's Guide to the Galaxy. Now, in terms of a term, I like this one I came across in one of the publications. They called it the hybrid age. Why is it the hybrid age? Because if you look at what our phones can do now, once upon a time, we would have had to purchase or make each one of these things on their own. And now they are all in our phone. That's really amazing. And I'm pretty sure I missed things on this list, too. This is just something I rattled off the top of my head. So what we're seeing now is really almost a consolidation of devices and melding of things that we used to keep separate all into one, at least that for the time being. So the question ultimately comes, and this is what we have to think about because it's really tough to determine where we're going to go in the future. So what's ahead? And I put question marks here because who knows? I know Google, for example, is doing a lot of robotics. Obviously, it's going to require printed circuit board design, possibly flexible circuit design. This, what they call also the surrounding of technology, where we wear it, not just hold it or sit in front of it. Okay? Are we going to see something in photonics, where instead of using electrons, we're now using photons, which are a lot faster? Is that going to completely change the way we do printed circuit boards? I don't know. What about wave technologies, where, to hell with copper, let's just have all these things communicate with each other just through remote frequencies? So we don't know what the future is going to bring, but obviously the printed circuit board, as we know it today, is probably going to change in the next 100 years. So that's the history for you here today. This is what I put here is what's ahead. We just don't know. But I think I'll just leave it with this here, that here at 9.Connects, it really is all about thinking about outside the box. So if you are thinking about something pretty wild and crazy and you want to bounce it off of us, don't hesitate, because that's what makes the innovation go forward. So thank you very much for your time today, and we look forward to having you join us at the webinar next month, and that is going to be on another design for manufacturing, and we're going to go into materials and layer stack up.